Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is chapter 4.4, which is trig functions of any angle. All right. So first, let's have a definition here. Let theta be an angle in standard precision with the point xy. So we want xy being a point on the terminal side of theta, and let r be equal to the square root of x squared plus y squared, and let that not be equal to 0. All right, so we don't want r to be equal to 0. So, well, let's get a visual here, and then we'll see what this can give us. All right, if I've got an angle in standard position, what we're saying is the vertex is at the origin, its initial side is on the x-axis, and its terminal side is elsewhere. So for example, let's say here. All right, so that's the terminal side. Here, that is our angle theta. This right here, that's theta. And we've got some point x comma y on the terminal side here. So let's say here, that is a point x comma y. All right. The last thing I'll add here is our variable r is this distance right here. That is r. All right. Now on that, if we have this, then we can say the following. Sine of theta would be equal to y over r, as long as r does not equal 0. That's why it's important that we have r not equal 0. Cosine theta would be x over r. Tan theta would be y over x. And here r can't equal 0, and here x can't equal 0. Not cosine. Cosecant would be r over y, and here y can't be equal to 0. Secant would be r over x, where x cannot be equal to 0. And cotangent theta would be x over y, as long as y is not equal to 0. All right. Now in here, well, let's see what this implies. All right. So in here for sine and cosine, r can't be equal to 0. So this distance must actually exist, is what it's saying. Now for tangent and secant, where x can't equal 0, we're saying, well, we cannot be on the y-axis. The terminal side cannot be on the y-axis. For cosecant and cotangent, where it says that y can't equal 0, what we're saying is that the terminal side cannot be on the x-axis. All right. Now, let's do some examples. So let's say that I have, let the point negative 2, 3 be a point on the terminal side of theta. Find the 6 trig function values of theta. All right, so let's see how we're going to do this. Well, first, let's go ahead and sketch this point. This point is at negative 2, 3. So that's, let's say it's something like this. Here's negative 2. Here's 3. So we have this point right there. And that point is on the terminal side of some angle theta. All right, we're assuming it's in standard position. So here's our initial side, and here is our terminal side. This right here is theta. So what we want to figure out here is all the 6 trig function values. Well, what did we need for all the 6 trig function values? Well, we needed the values of x and y, but also the value of r. All right, and remember, r is this distance over here, which is defined by essentially the Pythagorean theorem, or r is equal to the square root of x squared plus y squared. So in here, let's figure out what r is, because remember, this point right here is -2, 3. So r would be equal to the square root of -2 squared plus 3 squared, right? Because it's x squared plus y squared. And that would say the square root of 4 plus 9, which would be the square root of 13. So r is equal to radical 13. All right, so now we can figure out what sine theta is, because sine was the y value over r. So 3 over radical 13, which is 3 radical 13 over 13. Cosine theta would be the x value over r, which I can rewrite as -2 radical 13 over 13. Tangent would be the y value over x, so I'm going to do it this way. 3 over radical 13 over -2 over radical 13 is equal to just -3 over 2. All right, the radical 13s cancel out. Remember, when you divide by a fraction, you're multiplying by the reciprocal, so you would have the radical 13s cancel out. So that's sine, cosine, and tangent. Now let's look at cosecant. Cosecant was the reciprocal of sine, or you could think of it as r over y. So we would have radical 13 over 3. Secant was r over x, or in this case radical 13 over -2. And cotangent was x over y, which would give us actually x over y, which would be -2 over 3. And in fact, I should have done this one that way as well. If I had just looked at it as y over x, we would have gone straight to -3/2, right? Y over x. All right. So now let's do another one. All right. Let's say that I have given sine theta is equal to 4/5 and tan theta is less than 0. Find the remaining 5 trig function values. Of theta. All right, so in here, what I'm saying is we already have sine. So I don't need to find all 6, I just need to find the other 5. So let's see what we can do with this. Well, let's think about what it's saying. This is saying that we've got some angle sine where sine of that theta is equal to 4/5. Since 4/5 for sine, remember that sine was equal to y over r. That tells us that we're going to have two possibilities here. We're either going to have this triangle, or this point up here, where this is 5, and the y value here is 4. Or we're going to have this other point out here, where this is 5, and this is at the height of 4. All right. So what I'm saying is we've got these two possibilities. Either this is theta, or this is theta. All right. One of those two is theta. So which one is it? Well, we've also got this information. We're told that tan theta has to be less than 0. If you go back to this this thing right here, this tells you where each trig function value is positive, right? In the first quadrant, all of them are positive. In the second quadrant, it's just signing its reciprocal, cosecant. In the third is just tangent and its reciprocal cotangent, and in the fourth is cosine and its reciprocal secant. So since we know that tangent is supposed to be less than 0, well, it cannot be in this first quadrant because tangent is positive there. It cannot be in this second quadrant, in this third quadrant, because tangent is positive there. So it's either in the second quadrant or in the fourth quadrant. Now, it's impossible for it to be in the fourth quadrant because we have sine being a positive value, right? Remember, the y value was 4, positive 4. So the y value has to be above here. So it cannot be this one right here. So in fact, it must be that we're working with this one. Now, the question here is, well, how do we figure out what the x value is here? Well, you can think of this as some sort of triangle here. All right. If we think about this triangle right here, with this value right here being 4, that's the height of 4. Well, that means this height must be 4, right? And at that point, what we got to figure out is, what is this value over here? Well, we've got a right triangle, and we've got the Pythagorean theorem. So what we can say here is that this distance right here is going to be, well, I can say that a squared plus, I'm going to call 4b, so plus 4 squared is equal to 5 squared, right? So I'm going to say this is a squared is equal to 5 squared, which is 25, minus 4 squared, which is 16. So a is equal to plus or minus, well, 16 minus, 15, 25, there we go. 25 minus 26 is 9. So now we have a is equal to plus or minus 3. Now, which one do we choose? Well, the distance here is supposed to be a distance of 3 because we're talking about distance, but we're looking for the coordinate. We're looking for what this x value would be. Well, all the x values on this part of the graph to the left of the y value, or the y-axis, are negative. So this is actually a negative 3, making this point right here negative 3 comma 4. And now that I have that, we can say, well, sine theta was the y value over r. We already had that. Cosine theta was the x value, which we just found to be negative 3. So we have that over r, which is 5. Tan theta would be the x value over, the y value over the x value. Cosecant theta would be r over the y value. Secant theta would be r over the x value. And cotangent theta would be the x value over the y value. All right, so now we've got all of those values there. All right. Now, let's switch gears for a second. Let's talk a little bit about something called reference angles. All right. And reference angles is going to make our life easier in what we were just doing. So let's say, if I say let theta be an angle in standard position. All right, its reference angle is the acute angle theta prime formed by the terminal side of theta and the x-axis, all right, or the horizontal axis. All right, so what are we talking about there? So let's see what kind of different possibilities we can have. So if I have theta being an angle standard position, so it has to start in this side. If it ends here, so if it's in the first quadrant, well, this angle is already the acute angle between the terminal side and the horizontal side. So in the first quadrant, theta is equal to its reference angle. That's not very exciting. Let's look at what would happen in the second quadrant. In the second quadrant, if I have some angle here in standard position, so there's my initial side, and my terminal side is in the second quadrant, well, this right here, well, let's fix that. This right here is our angle theta, but this right here would be our reference angle theta prime. And you can think of it either going that way or that way. All right, so this right here is our reference angle. And now how will we find what this angle is? Well, in radians, we would say that the reference angle would be equal to pi minus theta, right? Because I'm looking to figure out what this angle is. I know that all the way across, all the way here, is an angle of pi. So to figure out what this would be, I start with pi and take away the original angle. In degrees, it would be 180 degrees minus theta. And by the way, over here, since theta is equal to theta prime, there's no conversion needed. All right, so that would be in the first and second quadrant. Let's look at the third quadrant. What happens there? So in the third quadrant, let's get our angle in the third quadrant. So there is my angle. We're talking about this being theta. All right. The reference angle in this case would just be this angle, because it is the acute angle between the terminal side and the horizontal axis. That's the acute angle there. Now, to figure out what angle this is, we're going to have to say, well, the entire angle minus the top half, right? So what I'm saying is this entire angle over here, if I just remove the top half, gives me just my reference angle. So it's going to say theta minus pi, and that would be in radians. In degrees, it would be theta minus 180 degrees. And finally, let's look at what happens in the fourth quadrant. Right, so if I have an angle here that is in standard position and ends in the fourth quadrant, the terminal side is in the fourth quadrant, in other words, this right here is my theta, well then my reference angle is the acute angle between my terminal side and the horizontal axis. So this right here is my reference angle. And in here, this reference angle can be found by taking, well, the entire full revolution and subtracting this, all right? Subtracting the entire angle. So it would be the entire revolution minus the original angle. In degrees, we would say, well, the entire revolution, 360 degrees, minus the original angle, all right? So that's how we find our reference angles. Now, let's just do a few quick examples of how to find the reference angle. All right, so let's say, I think I'm at example C. So, find the reference angles. So I said example C. Let's say that the angle given to me is, we'll do 1 in degrees, 213 degrees. All right, so, well, which quadrant is this in? That's the very first thing we need to figure out. So if we put this on the coordinate axes, well, we know that this is 0, this is 90 degrees, this is 180 degrees, this is 270 degrees, and this is 360 degrees. So 213 degrees would be, well, between 180 and 270, so somewhere around here. So if this is the angle theta that I'm working with, what I'm asking here is, what is this reference angle theta? Theta prime, excuse me. So that reference angle theta prime, we're going to say, well, in here, in the third quadrant, what was the formula? Theta minus pi, or theta minus 180 degrees. So we're going to say we have the original angle theta minus 180 degrees, which means 213 degrees minus 180 degrees, which equals 33 degrees. All right. Let's do another one, but let's do it in radians. Let's say that I have theta being equal to, I don't know, let's say 14 pi over 9. All right. So what we're going to do here is we're going to say, well, in which quadrant is this? All right. So let's think about this. Let's put this on the coordinate axis. And now what angle, where would this be? Well, in radians, this angle is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. All right, so we have 14 ninths. So that's definitely going to be either in the third quadrant or in the fourth quadrant. But the question is, in which one? Well, we really just need to compare 14 ninths to 3 halves. All right, so let's see. Between 14 ninths and 3 halves, the question is, which one is bigger? All right, because that will tell you where our angle really is. So the way that we compare fractions, what we can do is we can do a cross multiplication. So 2 times 14 is 18, and 9 times 3 is 27. And the thing about doing this is that it preserves inequality. So in here, since the right side was bigger, right, 18 is less than 27, that means this side is, oh, hold on, I multiplied that incorrectly. 2 times 14 is not 18. Let's fix that. Let's try that again. 2 times 14 is 28. 9 times 3 is 27. There we go. And now we have it the other way. Okay, good. So preservation of inequality still holds, is what I was trying to say. So because the left side was bigger than the right side, the left side is bigger than the right side. So that means that our original angle, 14 pi over 9, is bigger than 3 pi over 2, meaning that it has to be somewhere over here, the terminal side. So this is the angle that we're working with. Now, to figure out what the reference angle is, because the reference angle is this part, we're going to say the reference angle, well, from the fourth quadrant, if you recall, in radians, it was 2 pi minus theta. So the reference angle here, and I'll go back to writing white, the reference angle is going to be the full rotation, or the full revolution, which is 2 pi minus the original angle. So I've got 2 pi minus 14 pi over 9. In terms of ninths, in other words, coming up with a common denominator, 2 pi is just 18 pi, giving me here 4 pi over 9 as my reference angle. All right, so this right here, our reference angle, is 4 pi over 9. All right, let's do one more. Let's do one more, and then I want to make a comment about these. So if I had theta being equal to 4 pi over 5, all right, well, in here, again, I want to put this on my coordinate axes and say, well, in here, this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. The question is, where does this fall? Now, since the numerator is smaller than the denominator, it's definitely not on the bottom half, right? Because in the bottom half is when things are bigger than pi. So here, this is less than 1 whole pi. So we're either on the first quadrant or the second quadrant. Now, which one? Well, recall that this right here would be pi over 2, so half of pi. Half of pi, it would be equivalent to saying 2.5 pi over 5, right? Because 2.5 goes into itself once, 2.5 goes into 5 2 times. So this right here is just 2.5 over 5 pi. So 4 pi over 5 would definitely be on this quadrant over here. So that's one possible way to think about it. Another way you could have done it is the same way that we did this one, comparing the 14 pi over 9 and 3 pi over 2. But in any case, in here, we have our terminal side being in the second quadrant. So this is our angle theta, right? And our reference angle would be this angle. And in the second quadrant, what did we do? We said that the reference angle is pi minus the given angle. So in this case, it's going to be pi minus 4 pi over 5, which is just 5 pi minus 4 pi, and then everything over 5. 4 pi, yeah, there we go. Which gives me just pi over 5. So this angle right here would be pi over 5. All right. Now, why do we care about these reference angles? All right. So let's make a note here. Note. If I have f of theta, all right, when we're talking about that trig function, so maybe I'll start with this with a little bit saying, given f of theta is a trigonometric function, and by that we mean, you know, sine, cosine, etc., right? Just those 6. F of theta is equal to f of theta prime. So this allows us to work with our reference angle without having to look at the original angle, all right? So how is that helpful? Well, let's do some examples like the ones we've been doing earlier. And it just helps us to think about things better. It doesn't really change much, but it does help us think about things better. So that was E. So F. Let's say I had, if I said, let the point 3 comma negative 7 be a point on the terminal side of theta. Find the 6 trig function values. All right. So first the thing I'm going to do here is I'm just going to look at this point. So where does that point fall? Well, 3 negative 7 ends up being, well, let's say that this over here is 3. That's a 3. And this over here is negative 7. So 3 negative 7 would fall right there. All right. And what we can do with this is we can essentially build this triangle, all right, where this side over here, well, this part over here, this is the original data that it's talking about, but we can build this right triangle with a reference angle, all right? And let me just rewrite that. That's a 3. This value here is a 3. So in other words, this distance right here is 3. This distance right here is negative 7. That's a 7. And we can just go ahead and work with this triangle that we have here. What we need here now is our value of r. But we know from the Pythagorean theorem that r is equal to the square root of x squared plus y squared, which means in this case the square root of 3 squared plus negative 7 squared, which is 3 squared is 9, 47 squared is 49. Adding those up, we get the square root of 58. And that's a 5. All right. Now, from there, we're going to say, well, that doesn't really reduce, right? Because 58 is 2 times 29, so that doesn't reduce. So that's going to be our r value. So what we can do now is we can think of this as just right triangle trigonometry and say that sine of theta would be sine of theta prime, which is just simply opposite over hypotenuse, so negative 7 over the square root of 58. In other words, negative 7 radical 58 over just 58, because I'm rationalizing this. All right, and that doesn't reduce. Similarly, I can say just cosine theta Cosine is adjacent over hypotenuse, right? Because I can just go ahead and look at the reference angle. So it will be 3 over our hypotenuse. So 3 over radical 58, which will be 3 radical 58 over 58. And that's a 3. Tan theta would be opposite over adjacent, so negative 7 over 3. Cosecant theta would be the reciprocal of sine, in other words, hypotenuse over opposite, so radical 58 over negative 7. Secant would be hypotenuse over adjacent, so hypotenuse over adjacent, so that's radical 58 over 3. And cotangent would be adjacent over opposite, so 3 over negative 7. So essentially what this allows us to do is, this allows us to think of this as just putting this triangle here. So reference angles allow us to just put this triangle here and just work with SOHCAHTOA as we have been in the past, right? Similarly, I can talk about the first examples that we did that way. Let me show you. So in here, I could have worked with this triangle right here and said, well, if I was looking at my reference angle, this being my reference angle, I could have said sine would have been opposite over hypotenuse. This height right here would have been 3. The hypotenuse we found to be radical 13. So opposite over hypotenuse, 3 over radical 13. Look at that. For cosine, I would have said adjacent over hypotenuse, negative 2 over radical 13. Negative 2 over radical 13. Tangent, opposite over adjacent, 3 over negative 2. All right, so on and so forth. Same thing applies to this kind of problem. So let's do an example like this one with reference angles though. So that was F. Let's look at G. So let's say in G I said, given that cotangent theta is equal to negative 12/13 and sine theta is less than 0, find all remaining trig values. All right. So again, I'm going to start by putting this on the coordinate axes. Cotangent, we know from before that it was x over y, right? Because, yeah, and let me just remind you, I'm talking about here. Cotangent, it was x over y, all right? So since cotangent is x over y, what we can say is this is going to be just x over y. So this value right here is negative 12 over y being 13. That's if I take the negative to be 12. So I'm either looking at this, or I'm looking at what if I take the 13 to be negative and the 12 to be positive. So 12 to be positive and the 13 to be negative. Then this is the theta I'm looking at. All right. So the question is, which one are we looking at? Well, I have here that sine has to be less than 0. And if you recall from this little chart, sine is positive on top. In the first quadrant, all of them are positive. In the second quadrant, sine is positive. So because we have sine being less than 0, it cannot be on top. So it cannot be this option. Now, between these two, I mean, we already know it's going to be this quadrant, but think about it. Cotangent. Cotangent, we have it being negative. Here, tangent and its reciprocal is positive, so it wouldn't be able to be there either. So the only possible option is in the fourth quadrant. So let's look at this as if it was in the fourth quadrant only then. So this is the option that we're looking at, where this angle right here is the original theta. Well, we don't care about that angle. We care about the reference angle. And we're going to build this triangle here. And here, what we have is, well, the x value is 12. So this is 12. Right? And let me make that look better. And the y value is negative 13. Our radius, well, let's figure out what that is, or excuse me, our r. Shouldn't have called it the radius, but anyway, so r is equal to the square root of x squared plus y squared, which in this case really means, well, that's a square, the square root of 12 squared plus negative 13 squared, right? So 12 squared is 144, 13 squared is 169, adding those up, so 9 plus 4 is 3, is 13, carry the 1, 6 plus 4 is 10, and 1 is 11, carry the 1, 1 plus 1 is 1, and 1, excuse me, 1 plus 1 is 2, and 1 is 3. So we've got the square root of 313. Now, at this point, what we're going to do is we're going to apply that to our hypotenuse, all right? So when we do that, though, that means that this side right here is r is equal, well, I'm just going to leave it as r for now, because we know what r is. All right, so now we can figure out the 6 trig function values for this. So we have a sine theta, remember, it's the same thing as just working off of its reference angle, and it's going to be so, right, opposite over hypotenuse, so negative 13 over the square root of 313, which is going to be negative 13 radical 313 over 313. Cosine theta, which again we're going to be working off of just its reference angle, but I'm not going to write it that way. I'm going to say it's adjacent over the hypotenuse, which is just 12 radical 313. Ooh, too many ones. Radical 313 over 313. Tangent, opposite over adjacent, so negative 13 over 12, right? Opposite over adjacent. Cosecant. Cosecant was hypotenuse over opposite, so hypotenuse over opposite, so radical 313 over negative 13. Secant, which was hypotenuse, so radical 313 over adjacent, so 12. And cotangent, which was opposite over, this means adjacent over opposite, so 12 over negative 13. We already had that though, right? Negative 12 over 13 is equivalent. But yeah, so that's the 6 trig function values here, using the reference angle to look at this triangle. All right. I highly recommend that you do it this way, that you start looking at the reference angles instead. All right. And that's the end of 4.4.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.